All right, so let's continue. We wrote again the problem on the left side and the two Fourier cosine series which I anticipate I'm going to need before we proceed with the method of variation of parameters. So remember, that means we took the solution in the form of a series of these cosine functions, and the point is to determine these functions a naught of t, a n of t, dot dot dot, so that these becomes a solution of the boundary value problem. So we simply take this and plug it into the PDE. And let's just do this directly. And again, go slow and make sure you understand all the steps we're going to do here. On the left side, we're going to do partial t. Okay, so then partial t once, x is not affected. So on the left side, it's going to be a naught prime plus summation from 1 to infinity. A n prime, again, you could drop off t just to make it a little bit easier to write. And then cosine of n pi x. Now, very carefully, on the right-hand side, 4 is multiplied by partial x twice. Partial x twice will eliminate this guy. Okay, so partial x of a is not is 0. When I differentiate with respect to x twice, a n of t remains as it is. I should have wrote a n, but anyway. And partial x twice for cosine of n pi x becomes minus n pi squared cosine of n pi x. Lots of parentheses here, but I hope it's clear enough. Yeah, so cosine of n pi x prime or partial x becomes minus n pi sine. You do it one more time, minus n pi squared cosine. And then plus 1 is replaced by the corresponding cosine series. So 1 plus summation from 1 to infinity, 0 cosine of n pi x times t. So we're going to have to match the coefficients of cosines and, of course, the terms outside of the summation as well. So let's rearrange a little bit the terms here. And let's emphasize the term that's outside of the summation. So very carefully follow this part here, because a naught prime will be matched with whatever is left outside the summation. And then I'm going to combine these summations together so that it's clear how I can match a n prime from the left side. So a naught prime plus summation from 1 to infinity a n prime cosine of n pi x. Outside the summation here is just 0, so there's nothing else to write, 4 times 0. But here I have 1 times t that comes out of the summation. And let's put these two sums together. Summation from 1 to infinity. We can pull cosine of n pi x. So I'm left here with minus n pi like that, minus n pi squared times a n of t times cosine of n pi x. Yeah, so you pull cosine of n pi x, and you're left essentially with minus n pi squared a n of t as the coefficient. Now, second thing to do before we match the equations, let's deal with the initial conditions. Okay, so you're going to plug in t, 0 for t, into the linear combination we take here, so u of x0 equals a naught of 0 plus summation from 1 to infinity a n of 0 cosine of n pi x. This needs to be equal to x squared, which in terms of the Fourier cosine series in the same interval is 1/3. Let's bring this 4 over pi squared inside. So it's 4 minus 1 to the n pi squared cosine of n pi x. So now how do you find a naught? Well, you have essentially two differential equations because of this extra term on the outside. So look carefully. When we do the matching equations, what do we get? A naught prime. Again, if that's not clear that it's a function of t, you can write it of t, but you shouldn't need that. I mean, it's obvious that a naught, a n are functions of t. Say a naught prime of t equals t. And the corresponding initial value for a naught comes from matching a naught of 0 with 1/3 from the initial condition. So a naught of 0 equals 1/3. All right, that's the equation that gives you a naught of t. A n prime of t come from, going all the way back here, comes from matching the coefficient of cosine over here with the coefficient of cosine on the right side. So a n prime of t equals minus n pi squared a n of t. The initial condition for a n of 0, again, comes from the initial condition, so a n of 0 equals the coefficient of cosine of n pi x, which is, in my case, 4 minus 1 to the n pi squared. So we're lucky somehow that these equations are actually a little bit easier to solve than previous ones. This is just an exponential ODE. Okay, so I mean, let's actually deal with this one and then we'll get back to this. But look at the exponential ODE. I mean, I'm going to remind you here in this part of the page. This is just basically that quick ODE that we know from 270 dy dt equals some constant times y. Y is just c to the kt. Okay, if you want to remember that. So that's the same type of equation, except the k, the constant, is minus n pi squared. So you don't need to use the I1 and I2 formula, which we talked about in the previous lesson. It's more immediate than that. Furthermore, this one here is just an immediate integration. So a naught prime is t. You simply integrate both sides. A naught of t is going to be t squared over 2 plus a constant c. A naught of 0 is 1/3. So when we plug in 0 for t, we get that c equals 1/3. So a naught of t is t squared over 2. Oops, again, it's out of frame. So a naught of t, t squared over 2 plus 1/3. All right, so let's keep this in mind because that's going to be part of the solution. Here, as I said before, a n of t, it's an exponential, so that's going to be c, some constant, e to the minus n pi squared t. And because a n of 0 equals this, when I plug in 0 for t, c is going to be just this initial condition. So from a n of 0 equals 4 minus 1 to the n over n pi squared, we get that a n of t is 4 minus 1 to the n over n pi squared times e to the minus n pi squared t. So we're essentially done with the problem. Okay, so I'm gonna write it down nicely on a second page. So the full solution u of xt is a naught of t, which we determined before is 1/3 plus t squared over 2 plus summation from 1 to infinity a n of t, which is 4 minus 1 to the n over n pi squared e to the minus n pi squared t, and cosine of n pi x. It could be useful at some point to actually check your answer somehow. I mean, if you look carefully, I mean, like at least the boundary conditions, some of these conditions can be verified without writing too much on the page, just by looking carefully. So for example, when I do partial x, this is going to be sine of n pi x, right? So with some constant here. And if I plug in 0, that's going to be just 0. And when you do partial t, there's still going to be a t left here. So that means when I do partial x and plug in 0 for t, the whole function will be 0 as it should, right? If you look at the boundary conditions. This, if you want to check, it's not that immediate, but again, if I plug in 0 for t, you end up precisely with the Fourier series for x squared on the interval, the Fourier cosine series for x squared on the interval 0, 1. So it might be worthwhile to check either by hand or with Maple if you're or with some computer software if your solution is correct. On the last part of the lecture today, I want to go over another problem, which I don't know if we're going to solve it from top to finish, but I want to emphasize how one can combine some of the techniques we learned so far, namely the two techniques we learned in dealing with non-homogeneous problems. The translation method that we talked about before the second exam, and this method, the variation of parameters. So stay tuned for the last part.